very much.
Thank you.
Awesome talks. A little practical, okay.
That's more like
But it is totally dumbed down. So a couple things. I really appreciate, John and Christian, your talks. I'm fascinated, also yours, but hold on. I'm fascinated by where the difference is. When does FRCM, TRM as I like to call it, stop and FRP take over? What is that maximum tension that you can transfer? How many anchors can you add? How much can you really do? And I'll bug you later. And then I have some ideas. We've got to talk after this. I think I got some ideas in terms of that. Has nothing to do with this. All right. Let's see if I can get this to work. All right, that's me. So I've been working with FRP now for 31 years. It's hard to believe, I know, but in 1994 I started working in FRP. And back then, people said, how do you anchor the FRP? So people started talking about these FRP anchors. A lot longer ago than most people think. In the year 2000, Jose Restrepo was testing this at the University of Canterbury. U-wraps to anchor longitudinal, and U-wraps with and without fiber anchors, poorly detailed, but we were doing what we could. And that's really when it started a long time ago. So FRP anchors is what we have been doing, and we will continue to do so. They have some fundamental problems that really give me gray hair and ulcers. The only meaningful way to inspect these is to watch the person installing them. Everything they do, and then once they're installed, if you weren't watching them, geez, they might not even be there. That actually happened to me in the real world. So anyway, but yeah, pull that back so I can take a look at it, and oh my God, it's not there. Yeah. So there's no meaningful ways to inspect these. That's a fundamental issue, and I don't have the answer for it. We keep talking about it. So there's limits. There's scatter. If I take the exact same person, really good technician in a lab, in a controlled environment, doing fiber anchor after fiber anchor, massive scatter, and we do that. And same exact technician, perfect environment, perfect. So how do we anchor this in a way, one, that you can inspect it, two, that contractors will respect it. You hand these fiber anchors to contractors, they don't respect it. They think it's silly. And then when you're not looking, they install it with that in their mind. And then you imagine the scatter you get now. They call them horsetails and pigtails. And I'm just talking, this is it. This is the real world out there. And that they don't, but you hand a contractor this. And by the way, I know it's non-metallic, but I love the hybrid. I'm like, oh, that fits well, steel and FRP. So we came up with a hybrid. The problem here is getting the load from the laminate to your anchor, or in this case, the laminate to the plate. We've tried steel plates, we've tried composite plates, now we tried hybrid plates, and there's some detailing, but getting the load from the laminate to the plate is the trick. Getting the plate to the bolt, no problem. Bolt to the concrete, no problem. We got that pretty solved. So I don't like to read to people, so I'm going to let you, there you go, hope you read it. We came up with some designs. There's a few different permutations, and I'll explain these in a little bit. D2.5 and D8.25, so this has 8 holes. You don't need 8. You can just pick any 6, actually. Those you do need both. You need two half-inch diameters. And this is really designed with a concept of a lower profile, and we're focusing right now on collectors. Collector, pure tension element. How do you make that tension member better? How do you transfer those loads? How do you do it better? And, oh, by the way, you don't want to trip on it, and you want to put your floor and your rug down, so you got to have a flat. So these are the concrete screws. So we said, okay, let's do an exercise where I'm going to do an anchor, and I'm going to target the exact same force for each of these things. And so the first line is really an FRP anchor. So I'm going to target 30 kips. I want to pull 30 kips on that thing. All right. So an FRP anchor is very stiff, and you get to 30 kips, no problem. The red line is the 8.25 using, again, 6 concrete screws, any holes you want. And then the 2.5s are tremendous. And so we're like, ooh, it's ductile. So a couple things. Post-event, oh yeah, that saw load. I mean, there's no doubt. It's really easy to inspect and see, was it working? and especially dramatic on the 2.5s, but also with these as well. So we started looking at, like, how are we detailing these fiber anchors? And a lot of times, just 2 is not going to work. I'm going to need more to get to those 4. So do I offset them, which actually works pretty well if you have the space and you can do it. Or if you don't, I got to put them in series. I'll call this putting them in series. And the problem with this is that as you're pulling on this, these first set of anchors seize like everything. And so how do I sum up these guys? And if you start putting them closer together, there's some changes. But let's put them at 4 feet and play with this and say, all right, well, I really have to pick a displacement somewhere in here so that I can say that plus that plus that. That's the force that they're all contributing. And this is just, the fiber anchors are just they're linear elastic and they're very, very stiff. When we put these in series, we're like, ooh, this is working better. So now I managed to cut off my displacements. So, oops, when I reformatted it, I'm going to blame the formatting to the new, but sorry, I can't. No, that's what took me all the time. Anyways, point being, at a much larger displacement, you can look at, hey, I got that plus that plus that. And they're just working together better in series, much better in series. And then the 2.5s are even much more dramatic. They work really well. So this, I actually didn't think I included this one. And so just kind of in summary, they work well. You can see literally, physically, like, look at how they're working. Like each one doesn't work equally. There's a limit. And really 2 in series, I'm thinking is, I mean, we did test it up to 3, but there's no point in going to 4. We're not seeing that. And the maximum amount that we tested is an accumulated thickness of, I'm going to use inches, 0.16 inches. So everybody's pretty much standard weight carbon in this industry. That would be 4 layers, which realistically, you start getting more than 4 layers. I'm like, really? There's a practical limit there too. So again, I'm not a fan of reading to people. This is the test setup that we started with, and again, targeting collectors. It's not exactly a collector. You're restraining the concrete, right? The concrete's not so. But people have kept referring to these as collector tests, and all right, so here we go. But it's really a modification of the ACI with 355 type, if I'm not mistaken. Anyways, testing. And so this is just one of the, I decided not to have videos, but we're just pulling on this, and again, testing. We like this staggering. You could put them all in a row, but this chunk of concrete, I want it to kind of displace and I don't know, it seems to make sense. We haven't done a lot of testing with and without, but my fear is that it'll pull out a little sooner if all that concrete's all stressed right near each other. So the idea here is just look at it, the design's real simple, just look at each 6-inch wide strip. We just decided 6 by 6 for ease of shipping, handling, all that. Could we make them bigger? Yeah. Can we make them bent? Yeah, we've got 2.0, 3.0, lots of different permutations of this in the works. But if I take this and start pulling on it with 4 layers, the design strain of roughly 0.003, you do the math, you get about 45 kips. So if you take a 24-inch wide sheet, that's where these numbers are coming from. And these are actually really conservative. Those are reduced from quite a bit. But this is code approved, yay. It's got a piece of paper that says I can get a permit. Let me go back. But it's important. It's a necessary thing. If ICC or Atmo in the room, it's a necessary thing. And that refers to a design manual, and based on our testing, we have some advantages. We are currently just approved from a building code standpoint for the collectors, but that will change rapidly. And so this is just how you install it. For the 8.25s, you would install your laminate first. You could do it same day or wait till the next day. A little thickened epoxy, lay your plate down, and then drill, and then install your screws. And that's why if you, you just pick any 6. Pretty friendly too. I know some of the screw manufacturers will be like, no, never go at an angle and never back it out and put it back in. Well, we kind of did all that and it still worked. Just as fun fact, no problem. The 2.5s were really thought about. I didn't bring my sample. Anyways, this is more for overhead, right? This is going to be kind of hard to do. It's not impossible. We figured there's a rig we kind of came up with, but for overhead and vertical surfaces, and you don't care too much about a little bit of a bolt and nut sticking out, that's really what this was thought about for. It's just easier to do. So you would actually drill and set your wedge anchors first, then come back, and it just pops right through. You can just pull the toes aside when it's wet. If you haven't worked with the fabric, it's really easy to move around. Then come back, set your plate, and torque it down. Don't use the wrong, they don't use these in New Zealand. I learned this. They won't use wedge anchors in New Zealand because apparently the contractors will grab the wrong tool every time and over torque it. I didn't know that. That was new to me. I'm like, huh. Right. Well, it's making my shop drawing notes been like big, bold. You must use this to. Yeah. Anyway, so it's torque it down pretty easy. And so we're doing some large scale and full scale tests on this to validate it for other applications. In this case, a one-sided shear happens to be a diaphragm, and Virginia Tech's done a bunch of these tests. These are specimens 13 and 14, and the first 12 specimens were all FRP, sometimes different orientations, but effectively using unidirectional FRP. And then when they did use anchors, they used a variety of different fiber anchor type configurations. We were involved in several of those specimens as well. And then we're like, okay, we're going to buy 2 more. Now that we've learned all that from specimens 1 through 12, I need 13 and 14. I want to see if I can do something better. So what do you do? So I am now of the opinion that it's a good idea to not cover the whole darn thing. And this is actually talking to Tannerat and Oregon DOT. They'll force gaps for inspection. And if you look at a complete overlay on a slab, on a wall, on a column, you can't, yeah, that's true, yeah, you can't. I mean, there's cutoff, like if you're throwing salt on the road, I tend to not want gaps, but anyways, I digress. But I like the gaps, I put those on purpose, and we decided to try this. Let's do them at the ends and right down the middle, or mid-span if you like. See how that goes. That was 13. This was us rapidly heating it because we're like, we didn't want to wait, and we gotta go. So all the curing is temperature dependent. We were talking about FRCM, how long it takes to cure. That was an interesting conversation. I'm sure it's temperature dependent a little bit too on that 7 days, but so it's all temperature driven. And this is very, very, very post-peak. Eventually, all your cracks connect, and gravity takes the concrete to the earth, and now you're seeing through it. But when all of the anchors were still intact, it was only when the chunks fell, and then we flipped the whole. I took the sheet and pulled it apart and flipped it over. It's still got all the concrete. So there was no pull out. There were no anchor failures on anywhere. Really impressive performance in terms of the strains we were picking. This is where the strain gauges were. And we, especially in the next specimen, I'll show you, we got darn near rupture of the laminate. So it's operating to a larger strains, operating more efficiently. This was take 2. Okay, same amount of FRP. I just have bigger gaps. I kind of set it up differently. And the other parameter is I'm like, let's stagger where we're doing these. And in hindsight, I'm like, oh, of course this is going to be better. We kind of captured where the cracks could go in the other one. We kind of limited where they kind of hit that row in the middle, and I'll show you the crack pattern in a second. But this did work good. Oh, I lied. I did have a little time lapse thing here. So you can see us. We're really fast walkers. We'll get to the good stuff here.
Man, those grad students are more efficient than most.
Right? It's amazing, amazing. So we're starting to get, you can see the ACI debonding strain is where the dotted line is there. When you see the little white, you might notice little white chalk marks. Those we're marking debonded areas as they start. Anyways, and take it all the way. But what was interesting, what we loved was like, oh, wait a second. Every single other specimen, as many anchors as you want, as soon as it hit peak, it dropped. All of the FRP specimens. These were the only ones that held it. And that was very exciting. So this is actually post-peak before, you keep going. You got to keep going until it's pummeled. But after we hit peak and we had held it for a while, you're like, okay, hold on, let's go map it out and crawl underneath and look at the cracks. So still pretty good shape. Oh, you can see, by the way, some of the cases where we had to kind of move the screws and just work with it. And the cracking. the yielding of the screws themselves. You know, this is, you can rip them out. And I'm like, hey, check it out. You know, and it bites into the plate itself a little bit too. So that's ductility. We're not making FRP ductile, and nothing can make FRP ductile. But the performance we're seeing is much better, and we do get a little energy absorption from the plate and the screws themselves. So the black line is the I put control, but they tested 12 of these things, and so it was an analysis. So that was not data from an actual specimen, but they're wicked confident on this is exactly how that will perform, and that's a long story short. I wish Eric Jock was here. He would do a better job with his stringer panel models and all that
Is this
stuff.
control without any strengthening? Or
Correct.
twist? Okay.
Correct, yeah, just the bare, lightly reinforced. 4-inch thick, by the way. It's pretty thin. I didn't show you the full setups there, but there's little cord beams there to really center it. Anyways, this is 13 and 14. I did have these with a direct comparison from some of the published data from the other FRP, but it wasn't our test, and so I took it out. But it is published, and anyways, it does exactly what I said. So we basically, this is the fun takeaway from that. We hit the same peak force with half of the amount of FRP they installed. Well, 55%, but close enough. 55%, so they did full overlay, 2 layers of the same weight, same properties. We did 55% coverage, 2 layers, well anchored, hit the same peak that they hit, you know, and held it and absorbed more energy and had spacing so you can inspect it, and we're able to inspect all the anchors themselves. This is the crack patterns, and you can see how, staggering them. So more testing to be done. What's the right spacing? What's the max gap? I say, okay, 4-inch to no more than 18-inch. 3 times the thickness, but don't exceed 18. There's a limit. I like the smaller gap. Smaller gaps are better for sure. But we did get really good crack formation. Is it okay, like for example on a wall, should you be putting them where it'll crush, or should you move them in a little bit? I don't know. Talk to Wasim and some other people, but I think in those zones maybe you do move them in, but on the others you go to the. Anyways, there's just food for thought. You know, what's the best way to lay these things up? We did get well over 8 root F prime C. We went to 10, so that was a fun fact. And then just some kind of conceptual things that I thought I'd throw up here. Again, you see for vertical, we would probably be doing the 2.5s. And we have done actual projects. I just was getting tired, and I had to get my presentation to Celeste. And this is kind of some of the collectors. But we have done collectors. We have done actual projects in California. Yeah, that's it.